Hello students and welcome to the continued discussion and lesson on functions, and in this video we're focused on finding domain and also finding range. So let's look at the rules for finding domain. First we want to start with all real numbers, okay, from negative infinity to positive infinity, and the strategy is let's start with everything and then eliminate values that are invalid, that cause us problems. So eliminate values that lead to division by 0. Eliminate values that lead to non-real answers. We are not dealing with imaginary numbers in these functions. And then for real world problems, no negative measurements. For example, the diameter of a circle cannot be a negative number. The area of a square cannot be a negative number. And so let's jump right to it. Let's look at an example where we're asked to find the domain and the vertical asymptotes. So the first example here we have 4 minus x and then the whole thing inside of square roots. And let's start with all real numbers. Eliminate values that lead to division by 0. There is no division here, so we don't have to worry about that. Eliminate values that lead to non-real answers. So that's a possibility because we have a square root in here. So we have to make sure that everything that comes out of the square root, or that's in this radicand here, has to be a positive number or 0. So we know that 4 minus x has to be greater than or equal to 0. Because if you put a big number in here, let's say you put like 6 or 7, so let's try it on the side here. Square root of 4 minus 7, you would get the square root of negative 3, and this would be a non-real answer. Okay? And so that's going to cause us a problem. So we know that has to be true, and then we can just solve, and you get 4 is greater than or equal to x. In other words, x has to be less than or equal to 4. And in interval notation, we can write it as negative infinity to 4, excluding negative infinity because you can never touch it, and then going as far as 4. And for all of these problems with domain and range, it is highly, highly recommended that you solve it algebraically and also look at the graph. Neither graphing alone isn't really enough, and solving purely by algebra can sometimes be cumbersome and error prone. So if I have my TI-8384 graphing calculator here, and I've typed in square root of 4 minus x into y1 here, you can always see my window here. I've typed in some other stuff, but right now I'm really focused on y1. If you hit graph, you can see the picture of the graph. Okay, and here it doesn't have anything that approaches infinity when you approach this particular x value, so this would not have any vertical asymptotes. But you can see that for all of the x values, it goes all the way back here to negative infinity, and then it stops at 4. Now if you hit trace 4, you can see that it gives you an answer. If you try to type 4.1, instantly, you can see that here it's not going to give you any output at all. And that's because if you type in a value bigger than 4 into this function, you will get non-real answers. So now let's continue with a couple more challenging examples. So here I have an equation that says, or a function that says square root of 4 minus x over x squared minus x minus 6. And let's go through the list. Start with all real numbers. Eliminate all values that lead to division by 0. And I do have division here, or a denominator with variables in it, so I have to check that. Okay, so eliminating, so check for division by 0. And so I'm going to take this entire denominator here, and I have to say that, look, this whole thing, it can be whatever I want, but the only thing that it's not allowed to be equal to is 0. And then it turns out we can just solve this quadratic, and this is really just solving a quadratic, but instead of saying equal to 0, I'm just going to say not equal to 0, because that's what the domain is. It's numbers where x is not equal to 0. So we can factor this. This is x minus 3, x plus 2. It's not equal to 0. x minus 3 cannot be equal to 0. X plus 2 cannot be equal to 0. X cannot be equal to 3, and x cannot be equal to negative 2. So that certainly helps with my problem here. Next, eliminate values that lead to non-real answers. And again, I do have a square root here, just like in the previous problem, so I have to check that. I know that 4 minus x has to be greater than or equal to 0, so x has to be, so 4 has to be greater than or equal to x, or x has to be less than or equal to 4. Okay? And I know that all of these things are true, but it's kind of hard to say all of this. X is less than or equal to 4 except at 3 and negative 2. Especially if you're going to write it down in answers. Saying it might not make a big difference. So let's answer in interval notation. And I'm going to graph this on a number line first before I even attempt to try interval notation. So x is anything, so I'm going to put 4 on here. I'm going to put 3 on here. Well, I'll always like to put 0 and a negative 2 is important. So x can be anything less than or equal to 4. So that's what I'm dealing with here. However, x cannot be equal to 3. So it can be any of these numbers in here, but not equal to 3. So put open circle here. And then it also cannot be equal to negative 2. So it's like there's another open circle here. And again, this is not yet interval notation, but writing it that way certainly helps. So now I have 3 intervals. One interval on the left here, one in the middle, and this little segment here on the right. So on the left, it's everything from negative infinity to negative 2. In the middle here, between these two open circles, everything from negative 2 to 3. And then finally, everything from 3 to 4. The 4 is inclusive. And to see the graph of this, as well as to help us identify the vertical asymptotes, it's probably going to be at these 2 points, but we want to make sure. So let's go to our graphing calculator. And this time, I'm going to try to remove y1 here and work with y2 instead. So I've already got this pre-typed into there. Graph. You can see that it's slowly drawing the graph. Slowly but surely it's drawing it. And you can see that there's going to be a sort of a gap here. And by the definition of an asymptote, as x gets closer and closer to negative 2, f of x goes towards infinity. And it also goes towards negative infinity, and that's okay. Same thing on this side at 3. Okay, so I'm going to have to write this answer on the side here, since I'm running out of room, that the vertical asymptotes occur at x equals 3 and x equals negative 2. Okay. And there you have it, a problem that asks us to do something a more complicated. Find domain of this function using a little bit of algebra and using the graph to help us, and then also identifying the vertical asymptotes. And notice here, the vertical asymptotes and the domain are close, they're related, but they're not exactly the same. This 4 here doesn't have anything to do with the vertical asymptotes. What it does have to do with, though, is if you look at the graph, it doesn't go anywhere past 4. If I hit trace, I type in 4, I can get an answer. But if I type in like 4.001, just a little bit past 4, I get nothing. Okay? And so that's a good way to confirm that we're doing what we need to do. So continuing on here with our examples, we have example C, and we have a more complicated function with a polynomial on the top and a polynomial on the denominator. And here, we actually, as long as we're just looking for domain, we don't have to worry too much about the numerator. So I'm going to leave that alone, because you can put whatever you want into the numerator. It doesn't break any of these rules. It doesn't divide by 0, and doesn't lead to non-real answers. it's really the denominator that affects us. So let's check for division by 0. And of course we do that by setting the denominator here equal to 0 and seeing what happens. So x squared plus 5x minus 36 cannot be equal to 0. And let's just solve for x. So x, this can be factored, plus 9. X minus 4 cannot be equal to 0. We can split the two factors. And we get as our answer x cannot be equal to -9 and x cannot be equal to +4. And to help us write our final answer in interval notation, so you have -9 here, you have 4 here. It can be anything along this line, but the one thing that it cannot be equal to is 4 or -9. So to write our final answer with interval notation more clearly, we're going to say from -infinity to -9, and then from -9 to 4, and then from 4 to +infinity. Okay. And now let's go and look at the graph and see if we can find some asymptotes here. So let me go back. Let's go back into the y equals, and let me take out the second equation, and let me turn on the third equation. And we hit graph. You can see the graph being drawn there. And let me make this graph bigger because I have -9 and 4 in there. So let me make the window just a little bit bigger. Let's go from -20 to 20 in increments of 2. Okay. And when I graph it, help me visualize this a little bit better. So, being able to manage your window is highly, highly important in these types of problems, because you could easily cut off a very important part of the graph. And you can see here that there's sort of a imaginary line right here at +4. These are in increments of 2, so this is +4, and then one more over here at -9. Okay, and to confirm, just to be sure, so that it doesn't just seem like we're eyeballing it, if you hit trace, okay, let's approach 4 from the left. So if I type in, I don't know, 3.9, you see it gives me -28.775. Let's try 3.999. I get an even bigger negative number. Let's go one more, 3.9999. And I get an even bigger number. And we can keep doing this. You can type 3.99999. Let's try one more time with -9. So let's try going from the left to -9. So let's say -9.01. Whoops. Let's go to, I may have typed something wrong. -9.01. There we go. How about -9.001? And you can see the y values are just growing at a crazy pace right here. Let's try one more. Let's try -9.0001. And I get an even bigger number. And you can try again -9.0001, and you'll get an even bigger number because it's going towards infinity. Okay, so I can say that the vertical asymptotes here is x equals -9 and x equals +4. So these are my two answers. Let's try one more. This time let's try a fairly tricky example. Okay, so I have one more example here of finding domain and vertical asymptotes, and we can approach this in a similar way that we did before. eliminate values that lead to 0, eliminate values that lead to non-real answers, and we don't have to worry about this because there's no radicals, no square roots in there. So I know that the bottom here, x squared minus 25 cannot be equal to 0, x squared cannot be equal to positive 25, and x cannot be equal to 5, or x cannot be equal to negative 5. Okay? And this basically captures the domain. So we can draw this out on a number line to help us see this better. That you can have everything you want on the number line except at positive 5 and except at negative 5. So that means our domain is 3 intervals, everything between negative infinity and negative 5, everything in between negative 5 and 5, and then everything from 5 to positive infinity. Okay, let me fix my infinity symbol there. So that's our domain right here. Now we need to work on the the vertical asymptotes. And prior experience would suggest that it's going to occur at negative 5 and it's going to occur at positive 5. So let's look at the graph and see. So let's turn on the graph here, and then turn off the graph here and graph it. You know what? I have the window set to be something bigger than I want it to. So I'm going to hit zoom here and go down to item number 6, zoom standard here. Get the standard window. Things will look a little bit better. And again, we think that there should be a vertical asymptote at positive 5 and at negative 5. And you can kind of see the vertical asymptote here at positive 5. But a weird thing happens at negative 5. There doesn't seem to be any asymptote there at all. So that's a little bit unusual. One of these has a vertical asymptote. One of them does not have a vertical asymptote. So it seems you should, between positive 5 and negative 5, they should both be vertical asymptotes, but they're not there. Okay, and the reason for that, and you can try this, I'm going to hit trace and type in negative 5. And you can see that when you substitute in negative 5, you get nothing for the y value. There's nothing there. It's almost like there's a hole there. Okay? And so let's explore algebraically why that is. And what I'm going to do here is I'm just going to factor the entire thing. The top is actually factorable, and it gives me x plus 4 times x plus 5, and the bottom is going to give me x plus 5 times x minus 5, I'm sorry. And you can see that these two terms cancel. They actually cancel each other completely. However, you still cannot put negative 5 in here. If you do put negative 5 in here, you will get an undefined answer. So, while these two things look like they in fact do cancel each other, negative 5 is still not allowed to be in the domain. But what happens here at negative 5 is that you get a hole. Okay, so let me kind of erase this stuff here on the right side, and we can draw out this graph. So the graph looks roughly like this, where you have 5 here, you have negative 5 here, and it's going to be a vertical asymptote there, much like in our picture. Okay. But the left side of it doesn't have a vertical asymptote here at negative 5. Instead, it has a hole. And that's because the top and the bottom here are sort of being canceled. Okay, so I'll make a note here that since this action of canceling occurs, you get a funny thing here, and that's called a hole. So the domain that we wrote up here before is 100% correct. This graph is 100% correct. The only that's that's sort of unusual is that the vertical asymptotes and the domain don't quite match up. Okay? And so that's something very important to keep in mind. Okay, so we've talked a lot about domain and vertical asymptotes, and now we turn our attention to horizontal asymptote. And this is the formal definition. If the limit as x approaching infinity of f of x is equal to a, or if the limit as x approaches negative infinity of f of x is equal to a, then y equals a is a horizontal asymptote. So let's look at one possible scenario. So if you have something like this, a graph, where the behavior, and this is a f of x right here. Actually, let me use a different color. It's a lot easier if we can see this in a different color. Okay. So let's say you have this, and you have something like this. Or let me draw this a little bit better here. I don't know if you like what I'm doing. There we go. So, and I'd like you to turn your attention to these tails, not the vertical parts, but this end of the graph, where as we go towards the right, it gets closer to one of these, to a horizontal line. Okay, and so let's say there's like an imaginary line here that the function gets closer to, but doesn't quite cross. And so what this is saying is that if the limit as x approaches infinity, in other words, as x gets huge, y starts to approach a certain value, or as x gets huge but in the negative direction, y starts to approach a certain value, then we can say that this line here, y equals a, whatever this number is a horizontal asymptote. Okay. And horizontal asymptotes are very helpful in helping us determine end behavior and in also helping us to find the range of functions. Okay. And so we're going to look at a few examples of that.